Hi students, welcome to design and analysis of algorithm lab using Java. So today we would be looking into program number 7, Dijkstra's single source shortest path algorithm. Before we get into this algorithm of ours, we are supposed to have a basic idea about what is a graph, what is an edge, what is an vertex. A graph is nothing but a graphical representation of a given data. We have been already introduced to this data structure in terms of your data structures subject, wherein we are having a particular tree structure, data structures, right? So we represent that in terms of a graph. So you might have come up with respect to your DFS or a BFS methods, so wherein we have been using that graph. So already we have an idea of what is a graph. So here even with respect to edge and vertex, so even though we will just have a brush up of this prerequisites, that is graph, edge and a vertex. So here a simple diagram which represents 5 different vertex, that is 1 2 3 4 and 5 are termed to be as your vertex, right? So I'm just putting up those points here. Vertex is nothing but a particular point in a given graph, like it could be a node or a computer in terms of a computer networks. If computers connected in a network and you want to represent that in form of a graph, so we would represent each computer as a node and we would name it as a particular computer 1, computer 2 kind of a thing. So that is how it is. So vertex, so we name them to be as your vertex. Each computer in a given network would be considered as a vertex, and the connectivity between two computers would be termed to be as your edge or transmission media, right? Or if you are say suppose traveling from one particular place to the other, right, the directions what you take would be the edges. So from say place 1 to place 2 you want to travel, the path what you travel from one place to the other is termed to be as an edge. So that is in terms of your prerequisite. So we have a basic idea of your graph. Now what is this concept of uh, shortest path? So shortest path is termed to be as a optimization problem concept. So what is this optimization problem is nothing but whatever the problem we consider in terms of either minimizing it or maximizing the results would be considered as optimization problems, right? So this is termed to be as your optimization problem. So optimization problems would need a particular or approach to solve this set of problems, and this approach is nothing but a greedy approach or a greedy technique. So this particular approach of solving your optimization problems would be termed as greedy technique. So it is as good as any other technique like divide and conquer, what we have seen in previous cases of your merge sort or a quick sort, right? So that is with respect to your approach. Greedy technique is the approach for solving your optimization problems. Now with respect to like taking an example, right? uh, I have just put up a scenario here. Say suppose you have a particular problem and you have some multiple solutions to it. So we don't prefer looking into all of the solutions. Some given point of time, I don't want all the solutions to be looked into. So wherein it will be like time consuming if I go with respect to all the solutions, looking for all the solutions, isn't it? So we try to come up with only few solutions which are matching to our set of constraints or criterias, right? Say suppose I'll take an example here. Now I want to purchase a smartphone online, right? So what is the process we follow there, right? So we'll take that example in terms of right, these terms as feasible, optimal, optimality, all those stuff. So taking this example of online purchase of a mobile, So we'd like to put up some basic aspects of your greedy technique. Say I was putting a point of purchasing a mobile, right? So now first initial thing is I would look into the brands. So we have n number of brands in the market, isn't it? So if I'll not be purchasing all those set of brands mobile, so I would be only concentrating on particular uh, uh, budget actually. Not even in terms of the brand. First I look into like what would be my budget. So that is the main criteria here, right? So this criteria or constraint would be termed as to be as your feasibility aspect. So whether it is feasible in my budget. The next aspect I would be looking into in terms of the features. So even with the budget I would be looking at the other aspects that would be your features, like I want a particular 64-bit processor or 32-bit processor, isn't it? So in such way, so those would be the different set of constraints. So those set of constraints would be in terms of feasible solutions. Once you apply all these filters in your online purchase, right, you will be filtered out with less and less number of mobiles, isn't it? So once you look into, you find some thousands together at once, but once you put up all these criterias, isn't it? So you only find hardly 50 to 20 kind of mobiles, isn't it? So that is what we are trying to do. So we are following a greedy strategy here. Knowing or unknowingly we are doing that, but here we are separately doing it using this aspect or a approach for solving a particular problem. So out of this set of listed mobiles, these are termed to be as your feasible ones with respect to your budget and features, right? So I'll further scale down my requirements with respect to other set of options like cash on delivery, right? So all these, or a particular credit card, all those stuff, right? So again you'll be scaling down from 50 to hardly some 10 or 5 kind of a thing, isn't it? So finally, putting up all these constraints, we end up choosing one particular mobile, and that one particular mobile will be your optimal one, so which you feel that is the best one for you. So similarly we'll be doing this with respect to a particular given problem using a greedy technique, right? So this is what is the whole idea about greedy technique or a greedy strategy of problem solving. So we take up a problem and have a n number of solutions, but we'll not be looking into all the n possible set of solutions, but putting up some constraints, we'll try to scale it down to only limited solutions, and we call them to be as feasible. Once out of those feasible set of solutions, I'll again scale it down to only one final solution that would be called as optimal solution, right? So that is what is with respect to our greedy strategy. So next here we have just come up with uh, uh, algorithm aspect kind of a thing here, right? So here the algorithm is put up as a greedy itself. So wherein P indicates the problem, right? The problem what we are trying to solve, and N would be in terms of the number of solutions. It already I have some set of solutions. So what I'm supposed to do here is, out of those n number of solutions, I want to find out only the feasible ones first. So once I get the feasible ones, out of that I'll be choosing a minimum or a maximum result kind of a thing, right? What I've discussed previously. So here as you can see, P is a problem and n is the number of solutions for your given problem. So what do I do is start from 0th solution to the nth solution of mine and try to select the feasible one. See, x is equal to select of P. So I will be selecting each problem of mine and putting that as to be a feasible one. If it is a feasible one for me, so what do? I put that into a solution list of mine. So these would be the set of feasible solutions, as I was giving the example of purchasing a mobile, right? What did we do based on the filter aspect what we have put up? So only few mobiles would be added to the list. Similar is this algorithm, right? Starting from 0 to n possible solutions, I go on taking up the problem and checking whether that solution will be feasible to me. So this is what is greedy uh, technique algorithm actually. So I've just put up in terms of algorithmic aspect, right? So here greedy technique also have a particular equation. So with respect to, here I'm talking with respect to this slide in terms of our Dijkstra's shortest single source shortest path algorithm. So what is this equation all about? We'll be trying to trace that out in our example in the next slide. So here we are just looking into the terminologies what we are using and the condition. So it is similar to finding your feasible solution. If that is the case, in the second line, that is like say the first if condition is nothing but checking your feasibility. If it is feasible, so I'm just adding that to be your feasible solution. For time being, you just note it as the previous set of instructions what you have discussed. And here I have given some notations like what is v, what is u, what is d of v, and cost of v comma u. So here we are trying to reach out from one particular node to the other. So here I'll give one more example wherein a person is trying to reach out to a particular place. Say suppose I want to travel from my native place to a particular say Bangalore or Delhi, right? So how would I reach out to Bangalore or Delhi? So I would take up like by walk I can go or reach out to these places, by bus, by vehicle, personal vehicles, or by train, or by bus, or sorry, or by airways, right? So here I have multiple options, but out of this, so first thing I could put up is how would I reach out, right? So first I have to travel from my native to which point in the first case, isn't it? So I'm visiting a particular place. Say if I want to reach out to Delhi, so first point I would reach out is, say if I'm traveling by flight, I have to reach out to Bangalore. From my native I don't have any particular right airway is available. I have to reach out to Bangalore. From Bangalore I can take flight and reach out to. So this is how. So visited and unvisited. So now my native place would be the source point. From source point I am trying to visit a nearest place wherein I can catch up a flight is Bangalore, isn't it? So there, so I'll be marking that Bangalore has to be visited. So distance from my native to Bangalore would be pointed as d of v. So what is the distance I'm traveling from my source position to the intermediate position, that is Bangalore. So from Bangalore I would be reaching out to Delhi. So here I can't reach out Delhi from my native place directly, so it is unreachable, right? So there is all these annotations. So V is a visited vertex, U is a vertex which is right to the next immediate next, which is connected to the next vertex which I would be traversing to, right? So that those are all the things. So cost of uv would be the time taken, or in terms of the amount required, all these things. So cost would be the those things. So here we'll get a clear cut idea once we start with the example of ours. So let's move with the example here. So I have taken this example here wherein I have some 5 nodes, and each node has a weighted edges. So this is termed to be as your weighted graph. So already you might be having this idea, right? So weighted and unweighted graphs, but we are considering this as a weighted undirected graph, right? So again here, as you can see, I have just put up that equation of ours, right, for our comparison here, right? So we'll be starting with respect to, right, finding the shortest path. So here even with respect to what node I'm starting my traversal I have put up, that is to say source node is 1. So I put taking source point as 1. From there on I'll be traversing to all other set of nodes, like say 1 to 2, 1 to 4. So I am able to reach out directly, whereas with respect to 3 and 5 I'm not able to reach out directly, right? From this given graph I can reach out from 1, right? That is source node 1. I can reach out only to 2 and 4 directly, right? But whereas 3 and 5 are not reachable directly, so that would be pointed as unreachable. So that is what it will be u for us, right? So it will be like, so what I have put up in your previous equation, v will be visited, u is unvisited kind of a vertex, and cost of uv would represent that 5, 8, 7, 15, 10, whatever the weighted numbers we have. So those would be considered as your cost of u v to u, right? So gradually we'll get to know, right? Initially, like so first starting with the visited thing. So as I said, I'm starting from source 1, so I'll take that as to be as a 1. So what would be the distance from right, 1 to 1? Obviously 0, it doesn't have a cycle, right? So here from 1 to 2, as said, I have a cost of 5, so that I'm entering there, right? So here in the next case I am not able to reach out directly to 3, so I'm putting a infinity number, like say 999. So here I'm taking it as 999. We could take up even 99, right? Normally we don't take weights in terms of higher values. Hardly will take up some 20, hardly, right? So I'm taking this 999 to be as an infinite representation, right? So that is how normally we take some higher value for representing a infinity number. Now next, so 1 to 4, I'm directly reaching out from 1 to 4. So what is the cost incurred? 15. So that I'm updating it here. So here, so next is again 1 to 5, I'm not able to reach out, so that would put up as 999. So this is the initial cost incurred. So but out of this again, so where should I travel, right? Which path should I take? So this would be wherein I'm trying to update that in terms of here. So from where should I start my next journey, right? So as I was putting a point, so should I reach out to Bangalore, from Bangalore to any other place, or from Bangalore directly to Delhi, isn't it? So that is my problem now. So that is where now say d of u would be updated. Now how do I update that is also like say if d of v. So now where did I visit? Like, so I have visited from 1 to 2 and 4. So out of that, so I have to look into which one is the minimum first, right? So 5 is the minimum, so I'll just go to the that particular road. So 1 to 2 is my minimum cost, right? So I'll just take up that in terms of the route traveled, that is 1 to 2. So now I have visited 1 as well as 2, right? So the next visited list would be updated as 1 comma 2. So after reaching out to 2, so isn't it possible that I can reach out to 3? Yes, obviously. So what is the cost incurred? So that would be the upgradation or the uh, formula or the equation what we have put up. So d of v, so d of v in the initial, so I have visited 1, so plus cost of v or say, d of v would be 2, right? So I visited 2. So 2, what is the distance from the source node to 2? So that would be the case there. So in that case it would be 5 plus cost of v, so that is 2. So what is the cost of reaching out to 2 and from 2 to 3? Now I'm concentrating on the node 3. Why? Because after reaching to 2 I can reach out to 3, right? So I have to find out the cost there. So I can't reach out directly, but there is an intermediate route which I can travel to and reach out to 3, right? So that is what is the updation here. So initially self loop remains same as 0, so 1 to 2 remains as 5, but here we can notice that. So how did I come up with this 13 is, so you can look into the formula there. As I was putting up a point, d of v would be 2 plus cost of v is nothing but 2 comma u here would be the node 3 how that is 3. See now unvisited, right, or from vertex v, that is to say in the previous list out what we have put up, we said v is the visited vertex. Now what is a visited vertex in this case is 2, right? U would be unvisited vertex from the particular visited vertex, that is from 2. Which one is unvisited? 3, right? So I have to take the cost of that, right? Cost of u comma v. What is the cost of u comma v comma v? U, that is 8, right? So that I'm checking with respect to the previous one. What is the distance from source node to your unvisited node? That is infinity, isn't it? So initially we are taking d of u to be unvisited, right? So from source node I have not visited that, so it is infinity. So that is obviously less than your infinity. So if that is the case, what I'm trying to do, I'm updating that with respect to the cost which is minimum. When compared to infinity, 13 is less, right, or minimum. So that is what I'm updating. So this formula what I've put up in the first block is nothing but, right, a relaxation formula or a relaxation equation. So this would be followed for all your nodes and find out the minimum for all your respective nodes from a particular given source node 1. So 1 I have traveled to 2, from 2 I can travel to 3. So after reaching out to 3, right, so I can even reach out to 5. Yes, obviously. How? 1 to 2, 2 to 3, 3 to 4, 4 to 5, isn't it? So I can reach out to 5 on the same route, right? After reaching out to 2, I can reach out even to 5, right? So now look into, right, look into this aspect. So wherein we are trying to upgrade in terms of the set of numbers. So as previous thing has happened, so we are just looking into, right, the updated versions of your information. So here, see, after so I have 1 to 4 is directly 15, so I'm putting up that 15 as it is. So here as you can see, from 1 to 3 and 1 to 5 they have been updated, isn't it? So those are to say that from infinity at least we have come up to 13 and 30 with respect to 3 and third and fifth node, right? So similarly, so I'll just update that in terms of my result, that where is 1 to 2, 2 to 3. So what is the thing is 5 plus 8 equal to 13, isn't it? So 5 plus 8 is equal to 13. That is what I have put up. So now again I'll come up with choosing the minimum out of the remaining values. I've already visited 2, so I'll ignore that minimum value 5. So what are left out? 3, 4 and 5. The other nodes to be visited are 3, 4 and 5, isn't it? So 2 I have already visited and I know the minimum value for that. So I'll be ignoring that and only finding out the minimum with respect to 3, 4 and 5 nodes, right? So obviously 13 would be your minimum. So that is what would be the result there. So that would be upgraded with respect to visiting the third node, right? So I can visit the third node now with respect to cost being 13, right? So and 15 would be the same, so that will also be updated as it is, right? So that would be, now I've visited 3, now only left out is with respect to 15 and 30. So obviously 15 is the minimum one, so that would go as a resultant value, right? So these are the things, as you can notice that, right? So I'll upgrade the same things here, right? Now, so I've visited 4 now, right? So my visited list is 1 2 3 4. So after reaching out to 4, now just compare that whether yeah, or right, reaching out to 5 would be lesser than your previous values. See, now 1 to 4 is 15, and 4 to 5 is 10, so 15 plus 10 would be 25, isn't it? So 25 lesser than 30, yes, obviously. So what would I do is, so after visiting node 4, I would update the cost of reaching to fifth node as 25 rather than 30. So now the left out final node to reach out is 5. So obviously I know the result already. Isn't it? So I'll just go with respect to the values there, right? As you can see that we have come up with the final solution as, right? So it would be 1 to 2 as 5, 1 2 3 as 13, right? 1 to 4 as it is, wherein there is no other alternative or other minimum route I can reach out to 4. So 15 is the minimal, so that remains the same, wherein we are not updating it, right? So but once we reach out to 4 and find out that I have a minimum path reaching out to 5, right? So that would be updated, so 25 would be updated rather than 30. So rather than going out from 1 2 3 and 4 and 5 for the route 5 from source node 1, so I would take a rather a short path, which would be 1 4 and 5, right? So that would be the final solution. That would be the final solution for your given graph, right? So this is the final solution of the given graph, that is 5 13 15 and 25. That is to say 1 to 2 would be 5, 1 2 and 3 would be 13, 1 to 4 would be 15, and 1 2 1 4 and 5 would be 25, right? That is the final solution what we get out of this particular given graph, right? So this is the final solution what we have. This would be considered as your optimal solution, right? We have tried to come up with, say, for node 3 and 5 from infinity to 13 and 25. So isn't that a minimization problem? Yes, obviously. So we have used a greedy technique with respect to finding the single source shortest path. That is to say, given single node or a starting point, we have to reach out to all other nodes in a given graph and find out the least cost. So this would be the least cost solution for us, or the optimal solution for a given graph of Dijkstra. So this is your assignment, guys. So just try out with a similar graph with different weights given, wherein you are supposed to start with different nodes. We have tried solving it from source node to be as 1. So you try out with respect to source node 2 3 4 and 5. You would be getting different set of possible or optimal solutions, right? So please try out and then go for your programs. And one more note to be made here is, first come up with a graph. Don't blindly give any input to your program, and moreover your input should be in a matrix form, right? Your input should be like rows and columns, right? So it should be in a matrix form, wherein the weight should be given in terms of uh, a tabular way, right? So as you have done that in terms of your DFS or a BFS program of your data structures in the previous semester, right? So that is with respect to your assignment, and submit this once you complete this video, and try to analyze the things and post it in your Google Classroom, right? So I've also started a YouTube channel on my name, that is Sri Shelnath. So you can just subscribe to that for your regular updates on your lab programs. Thank you guys.